Okay, we looked at the Dijkstra's algorithm for single source shortest path problems. And let's say we want to augment this and say now, not just from one source, we want to perform what is called the all pairs shortest path. So let me tell you what I mean by this path problem. See, in this graph that we were given, we were given distances from every vertex to every vertex, right? Vertex to every vertex. So the idea is, can we, we want to create a table of, let's say, distances between all vertices. I mean, typical example will be, let's say we're given the flight time let's say given flight duration, like basically the edges correspond to flight duration. Flight duration, we may want to create a table. Create a table which tells you what is the shortest flight duration possible between a pair of cities. Something like Clear Trip or Make My Trip actually does this today. So, and this problem is called the all pairs shortest path problem, APSP, as opposed to SSSP. So, basically, let's say that means we're given, let's say nodes correspond to cities and edges correspond to time. Okay. And you want to find the shortest time required to fly from any city to another. Okay. We again assume the graph is G of V comma E, which is a set of vertices and edges. And these edges are stored in a cost matrix, C of V comma W. The all pairs shortest path problem finds for each pair of ordered vertices V comma W, the smallest length on any path from V to W. Okay, so you want to find for every ordered pair of vertices. So we can solve this problem using Dijkstra. Okay, and where each vertex in turn becomes the source. And of course, we will have an order enqueued algorithm. Okay. But there is another nice, although this is also as complex, there is a more direct way of solving it. Using what's called the Floyd's algorithm, which is called the Atsp algorithm. And the idea is very nice. The way it works is this: we assume that vertices are numbered. We map them to numbers. The labels of the vertices are mapped to numbers. V is equal to 1, 2, n. And then we use an n by n matrix A, which computes length of shortest paths. Okay. Initially, we set A of ij equal to C of I comma j, I naught equal to j. What is C of I comma j? Which is the usual original matrix that we had as in the Dijkstra's algorithm. If there is no path from I to j, C of ij is set to infinity, just like we did in the single source shortest path. Each diagonal element is set to 0. Then we make n iterations over the matrix A. We'll see an example, okay? Matrix A. After the 8th iteration, the idea of this algorithm is primarily this. After the kth iteration, A of ij will have for its value the smallest length of any path from I to j that does not pass through a vertex numbered higher than k. This is the most important part. Higher than k. This implies I and j can be any pair of vertices. Okay. Any intermediate vertex on the path must be less than or equal to k. What we do is, in the kth iteration, we do the following. A of k of I comma j equals min of ak minus 1 of I comma j, ak minus 1 of I comma k plus ak minus 1 of k comma j. This is primarily the idea. Okay. The subscript k script k denotes the value of the matrix A after the kth iteration. This is the most important point. Okay. Now what we'll do is, let's go back to one graph that we had, maybe slightly different. We had this graph yesterday, remember? Let's see how this works. Let's start with the matrix. So initially, we have something like this. Say 1, 2, 4, 4, and 5. So we start updating this matrix. So initially we set it to A of I comma j is 0, 10, 1 to 2, infinity, 30, and 100. Infinity, 0, 50, 2 to 3, infinity, infinity. 3 has a path to 5, 10. All others are infinite. Then we have 4, finite, infinite, 20, 60. And 5 has no paths. So this is your initial matrix. So the next, for example, when I look at A1 of I comma j, this will be the same. This was A0. We started off with this. I comma j will be equal to A1 of A0 of I comma j, no change, because there is no path from 1 to there's no path from 1 to any node. Okay, there are only paths. I mean, what I mean is there's no via this. Okay, so we already have this over here. I mean, there's no way of, what I mean is there's no entry to, see what we're looking at is we're looking at if there's a path from 2 to 2 to 1 or 3 to 1 or 4 to 1, which will lead to a shortest path, and we don't have that. Okay, so A of 1, I comma j will be the same. Now let us look at A of 2 comma j. I comma j will become I hope I'm doing it correctly. If there's any mistake in my arithmetic, please correct it. So I have 0, 10, going via 2, right? So I can go from 1 to, see, now there was no path from 1 to 3. So, but now I can go from 1 to 3 via 2. Okay. So this path gets updated. So I have 60 over here, 30, 100, infinity, 0, 50, infinity, 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 0, infinity, 10. Correct me if I'm wrong, because there's only one path from 2 to 3. 20, 0, 60, infinity, infinity, and 0. Now let's look at, so this is when I included the node 2. Now what happens when I include the node 3? We'll see a change now. That means what? Notice that I'm looking at any path from any of 1, 2, 3, 4, 5, but having a path through 3. That's what we are looking at. And what do we see here? We have going through 3. So there's no direct path. So this is 1 to, this one is still going to be 10. And this is going to be 60 still. So I've included only 3 and there's no path from 1 to 3, 60, then 30, 1 to 4, there is a, sorry, this was 30, right? It's already there, 100. Now, because I included 3, now 2, for example, 2 to 3 is 50, right? Yeah. 2 to 1, there's no path, 0. And 2 to 4, there is still no path. And, but 2 to 5 will get updated. 2 to 5 will become 60 now. Okay. Infinity, infinity, 0, infinity, 10, infinity, infinity. Going via 3 doesn't change things very much. Yeah. There's only one path. 2 to 5. Okay. 20, 0, infinity, 30. And this is A3. Okay. So this is A3 of I comma G. Now, if I include A4, the fourth vertex, let's see what happens. 5. It will become 0, 10, 50, 30, 1 to 5 is 30, 1 to 5, yeah, 30, 20, 50, 60, correct. And infinity 0, 50, infinity 60, infinity, infinity 0, infinity 10, infinity, infinity 20, infinity 30, infinity, infinity. 1, 2, 3, 4, 5, 1, 2, 3, 4, and 5. And this is A4 when I'm including the fourth vertex. And A5 of I comma j, because there is no path via this, will be equal to A4 of I comma j. So now what do we have? We can read off. What is the distance from 1 to 2? This is the shortest path. 1 to 3, this is the shortest path. 1 to 4, this is the shortest path. 1 to 5 is the shortest path. 2 to 5, 2 to 3, 50 is the shortest path. And 2 to 5, we have 50 plus 10, 60. And 3 to 5, there's only one shortest, 10. And 4 to 3, we have 20. And 4 to 5, we have 30, because you can take this particular path. So originally it was 60, and then it goes to this, and so on. Okay. So this is essentially what we do. So this is the all pair shortest path algorithm. Let me write the procedure module for you. Module Floyd, and let's say we pass the matrices A and C. So we initialize A of I comma j, C of I comma j, whatever is the initial matrix that we have. Then the outermost loop, do 1 less than or equal to k less than or equal to n, do 1 less than or equal to I less than or equal to 1 less than or equal to j less than or equal to n if A of I comma k plus A of k comma j, previous iteration, is less than A of I comma j, then we update A of I comma j is A of I comma k plus A of k comma j. End if, and end do, and end do is your function for, or procedure module for computing the Floyd algorithm. Again, figure out how to keep track of paths, and this algorithm is, this also is attributed to Warshall, and this is called the Floyd-Warshall algorithm. And although, you know, if you look at the all pair shortest path versus the single source shortest path, using it repeatedly, the complexity does not change very much. This uses a particular strategy called dynamic programming. Why do we say this? It breaks down the problem into sub-problems and then combines the answers. Let me tell you what I mean by that. And it's extremely useful in networking, where again you're looking at shortest path. And what do I mean by combining smaller problems is primarily the following, that if you look at it here, if you look at this part over here, so what we're doing is we're looking at a lower numbered vertex. First you solve it. If a lower numbered vertex gives you a shorter path to another destination, that gets corrected when you go to the higher numbered vertex. So basically systematically go through the lower numbered vertices and keep on updating the. So notice that this is a of I comma j is a of I comma k plus a of k comma j, two smaller subproblems. Now a of I comma k can get updated when it goes through the iteration, and it finally gives you the final solution to the problem. Okay. So this uses this idea called dynamic programming. Let me stop here.